Whenever you see one of those little glass vials of medicine, it's easy to think it's just a bottle. But what you're actually looking at is the very last step in an unbelievably complex journey. And ensuring that simple vial is perfectly safe, well, that's a hidden science of insane precision. So let's pull back the curtain and dive in.
Everything starts right here. Long before a single drop of life-saving medicine ever touches the glass, each vial goes through this intense, high-pressure wash. The whole point is to blast away any tiny particles or microorganisms using something called water for injection, or WFI. It's basically the purest, most pristine water imaginable. But getting there is anything but simple.
And that really begs the question, doesn't it? How clean is truly clean? Because in the world of sterile medicine, clean isn't something you can just see with your eyes. It's measured on a microscopic, even a cellular level.
And this is where it gets tricky. Here's the massive paradox these manufacturers are up against. The very detergents they need to get the vials sterile can be toxic to our cells if even the tiniest, most microscopic trace is left behind. The thing that's supposed to help can actually become the problem.
So that brings us to our first big hurdle, the invisible threat. This is that moment when the cure actually becomes the contaminant.
Now, this risk has a specific scientific name, cytotoxicity. It's just a way of measuring how toxic a substance is to living cells. We're talking about incredibly small amounts here. International standards are so strict that even a microscopic residue is considered a potential danger. That's why proving these vials are perfectly rinsed isn't just a quality check, it's a fundamental promise of safety.
Okay, now check this out, because this is fascinating. A study looked at a bunch of common cleaning agents, and it turns out they are not all created equal. Not by a long shot. Most of them were fine once they were diluted, but some, like this one they called enzymatic C, were still highly toxic to cells even at super low concentrations. This just shows you, with crystal clarity, why that rinsing process has to be absolutely, positively, 100% perfect.
So, how do you even begin to fight a threat you can't see? Well, you do it with a machine that has to survive an incredible series of tests. Think of it as a machine's gauntlet, a brutal process to prove that it works. And to make sure every single machine is up to the job, there's this really strict process called qualification. It's not enough for the machine to just work. You need a rock-solid, documented paper trail that proves without a shadow of a doubt that it was built right, it runs perfectly, and it can be trusted to do its job the same way every single time. It's all about protecting patients. And this isn't just one test. Oh no. Qualification is much more like a machine's final exams, a 5-step gauntlet that it has to pass before it's ever allowed to touch a vial that could end up in a hospital.
The whole thing unfolds in 5 really logical stages. You start on paper, figuring out what you need the machine to do, that's the user requirements, and then proving the design can do it. Only then do you get to the physical machine, with checks for installation and operation. And the grand finale is performance qualification, proving it works under real-world conditions. You have to pass each stage before you can even start the next one. It's like building a chain of evidence.
Right, so the first 2 stages happen before a single bolt is even turned. The URS is basically the wish list. It defines exactly what the machine has to do, like must wash 240 vials per minute. Then, the DQ is the blueprint check, where engineers prove on paper that their design can actually deliver on that promise. All this before anything is even built.
Then the machine arrives. Next up is installation qualification, or IQ. And just look at the level of detail here. This is so much more than just plugging it in. Engineers turn into detectives, physically checking every single part, every motor, every valve, every weld, against the drawings to prove it was built and installed exactly right.
After that comes the OQ, or operational qualification. This is basically the machine's stress test. This is where they get mean. Technicians push it to its absolute limits on purpose. The highest pressures, the fastest speeds, the absolute worst-case conditions. They're trying to find the boundaries, to create a proven operating window where they know it will perform safely, even on its worst day.
And that brings us to the final exam, performance qualification, or PQ. This is the moment of truth. The machine has to run with actual vials and pass with flying colors, 3 times in a row, no exceptions. Why 3? To prove it wasn't just a lucky shot. It's the ultimate proof that this machine can deliver perfectly clean vials, not just once, but consistently, reliably, batch after batch after batch.
So the machine has passed every test. It's a certified genius. But think about this for a second. To wash a vial, the machine has to hold onto it with these grippers. And you can't wash the spot you're holding. It's a fundamental challenge, right? And it shows exactly why you can't just qualify the machine in a vacuum. You have to understand and validate the entire process from start to finish.
And that very idea that you have to think about the whole process leads us to a much bigger core philosophy that drives all of modern drug manufacturing, building quality in.
It's all summed up perfectly in this guiding principle. Quality cannot be tested into a batch of product, but must be built into each stage of the manufacturing process. In other words, you can't just cross your fingers and hope for a good result at the end. You have to design the system so that a good result is the only possible outcome.
So this idea, GAMP, it isn't a single rule. It's a whole mindset. It's a framework that forces companies to think about the entire picture, from the materials they buy, to the machines they build, to how they train their staff. It's about creating the system so controlled and so robust that safety isn't an accident, it's an inevitability.
And this commitment doesn't just stop once a machine is up and running. Oh no, we're talking about a lifetime commitment, because in this world, validation never, ever ends.
And the FDA has this fantastic model that shows you exactly what we mean. They see it as a 3-stage life cycle. Stage 1 is process design, where you map everything out. Stage 2 is process qualification, and yep, that's where our machine's 5 big exams take place. But look, there's a crucial 3rd stage.
Stage 3 is continued process verification. This is the long game. It's an ongoing promise to keep watching. For the entire life of that product, they're constantly collecting and analyzing data, looking for any tiny deviations. It's how they make sure that the process that was perfect on day 1 is still just as perfect on day 1000.
And this isn't just an American thing or a European thing. This is a global promise. These tough principles of validation are recognized all over the world by groups like the World Health Organization to make sure that no matter where you are, the medicine you rely on is safe. So you see, from the tiniest detail, like one single machine passing its 5 big exams, all the way up to the massive picture of a product's entire life cycle, every single detail is planned, proven, and validated. And it's all for one reason: to protect the patient. Which really leaves us with one final thought to ponder. In our world of mass production, where millions of doses are made every day, what does it really take to guarantee the safety of that one single dose that might save a life? The answer is this invisible, incredibly demanding, and deeply committed world of science and engineering working behind the scenes every single day.